This presentation is about a ground source heat pump system in a large home. And it's sponsored by IGSHPA, Down to Earth Energy, the International Ground Source Heat Pump Association. We want to honor the earth with this presentation. And this is by Gerald McLean, and it's a 5-year report on results. I am the Distance Learning Coordinator for the International Ground Source Heat Pump Association, and this is my home. Well, a ground source heat pump system makes energy sense, and this is sort of why. You take 1 kilowatt of energy from the utility, and you take 3 to 5 kilowatts of free energy from the earth, and you take those two and put those together, and you'll end up with 4 to 6 kilowatts of energy for the building. Well, that essentially gives you a 400 to 600% efficient, or a COP of 4 to 6. COP is coefficient of performance. This is what the house looks like once it was finished, and this was actually right after it was finished. It's located at 3708 West Deer Crossing Drive in Stillwater, Oklahoma. New construction was in 2010. The 5-year results of ground source heat pump system, and you can find it online at youtube.com, and you search for IGSHPA and look for homes 1 through 6, and you'll actually see the construction of the ground source heat pump system for this home, from the drilling to the finished product. That's what the house looked like as it was being built. You notice the large poles there holding the roof up. It is a closed loop ground source heat pump system with a dew superheater. The foundation was actually poured on December the 26th, 2008, day after Christmas. The home size is around 6,000 square feet, a little bit larger than that. Layout is actually a 2-story building with ductwork in the attic space, unconditioned space. The heat pumps are on the 2nd floor in the attic space. It's setting on 2.5 acres. The recommended tonnage was for 9 tons. So it ended up with ground loop, 6 loop boreholes 300 feet deep. It has 2, 3, and 4 ton heat pumps. Moved in June the 1st, 2010. I had 5 bids to install heating, cooling, and hot water system. And I was looking for conventional system as well as the ground source heat pump systems in the bids. So the final accepted bid for the ground source heat pump system was in 2009, and it was for the complete installation of ducts, units, loop field, all new construction for a new constructed building. So it's for everything. A conventional system, a gas system, electric, would have cost $30,000 for this. The ground source heat pump system, 9 tons, 3 units, 2, 3, and 4 ton. The loop field were 6 boreholes 300 feet deep and 1-inch HDPE pipe, which was $8,100. The headering was $4,124. The inside piping was $3,912. Unit delivery was $17,697. That was for the 3 units. The rough end or final was $9,084. The final and startup was $2,402. So you have a total of $45,321 for the system. With the 30% tax credit, I was able to take off $13,599 and $200 per ton from the local utility in Stillwater, Oklahoma, was $200 per ton. So had 9 tons, so that was $1,800. So the total cost for the ground source heat pump system was $29,922, which is very close to the conventional system that could have been installed. The final cost for the ground source heat system was actually less than that conventional system, and the projected annual cost was $959 a year, or $80 per month. Contractor information. This was from ComfortWorks, located in Goldsby, Oklahoma. It's actually 82 miles from Stillwater. HVAC specialty is ground source heat pump systems, and they are IGSHPA installer certified. President is Chris Ellis. Background information. It was established in 1975 as C&S Heating and Cooling Air Conditioning. It was sold in 2007 and became ComfortWorks Incorporated. Here is their web address, comfortworks.us. The equipment that was used was Climate Master Tranquility 27. I particularly wanted Climate Master because Climate Master is manufactured in Oklahoma City, which is about 60 miles away from Stillwater. So I particularly wanted a Oklahoma company. And so this is the unit. There were 3 different units, a 2-ton, a 3-ton, and a 4-ton. It does have, as you can see there, a Copeland 2-stage uploading scroll compressor, variable speed blower motor, E-coated air coils, foil face insulation in the blower section, fully insulated compressor section, 2-inch filter frame with high performance MERV 11 pleated air filters, stainless steel drain pan for longer life, unit performance signal automatic alert system lets you know if the system is not running at peak performance, exclusive spring, double spring, and grommet compressor isolation for ultra quiet operation. And it has easy to lift out service panels with stainless steel front panels. The Tranquility 27, this is showing the 2-ton unit, the 3-ton unit, and the 4-ton unit. And the information about them is for the ground loop heat pump. This is for the cooling, and you can see the capacity, the EERs there, and also for heating, the COP. Okay, blow that up a little bit, you can see it a little bit better. This is the location for the drilling and preparing the property, and this is my home, and the drilling was calculated to be about 15 feet away from the house and 25 feet apart. The first drilling site was right there, sort of to the front edge of the building at the time. I had concerns for containment of mud and runoff water in the street and adjacent property. We'd had a lot of rain that spring, and there was a lot of water and mud coming from my property because of construction and running into the gated area. And I had to clean that out about 3 times because of that. So the recommendation was for 3,600 feet for the loop field. So the site needs 9 tons, so 6 boreholes will be drilled to 300 feet for a total of 1,800 feet using 1-inch HDPE pipe. The recommended spacing between the boreholes was 25 feet. All underground utilities were flagged prior to drilling and digging. This is the drilling location again, preparing the property, but you can see the different component parts there. There's a small flag there. That's all the drill sites were measured and located prior to drilling. And the drill pipe was marked off so that they wouldn't put more than 300 feet of drilling pipe in the ground. So they wanted to make sure that was right. So the rest of them were taped off so they couldn't be used. Mud ring was used, and then a short casing was used. Now, one of the things that happens, you notice the drilling rig in the very back here. This was drilling the first borehole. You notice all the brick there in front of it. Uh-oh. And I'm going to drill in that area. So I had to move all that brick, you know. So the drilling rig was brought into the site. Site had to be cleared and ready for drilling. Bricks had to be removed. So I spent the morning getting all the bricks moved while they were drilling their first hole. Cuttings in the form of mud may come from the borehole, so I had to make sure that there was a ditch and everything for the runoff, as you can see there. And of course they supplied the ditch and everything, and I showed them where to run the water off into part of my property. And you can in a city use a reclaim unit to contain the cuttings and keep it from going into sewer drains and things like that. The deer crossing is set on a 2.5 acres and had adequate area for runoff without going into the street or the sewer drains. So you can see that first arrow there. Those bricks had to be moved. There's the cuttings runoff, and that was mud from the borehole being pumped out because water was being used in drilling, mainly clay and some gravel down lower. The heat exchanger pipe was 1-inch HDPE pipe. It's thermally fused, the U-bend on the end. It's a total of 610 feet long, so it's 305 feet on each leg of the coming back up to the top. This was filled with water and pressure checked to make sure that the U-bend didn't leak and there was no leaks in the pipes. And once those were filled and the ends were bent over on the ends of them and taped off to keep the water in the pipe. Then over here you see the spool being used to lower the HDP pipe into the borehole. And before they did that, they actually attached a 1-inch by 8-foot steel rod on the end of that to give it more weight, so it's going to go all the way to the bottom of the hole. So 600 feet of 1-inch HDP pipe in the borehole with about 5 feet sticking out. Grouting of the boreholes, they had a mixing truck that had all the mixing of the grout, and we used BH20 grout, and BH stands for Black Hills. It has a 20% solids. It's a modified bentonite grout, which requires no polymer additives and is a complete mineral-based product. Once placed, the grout will set into a semi-rigid plug of the borehole. Of course, the reason for that grout is to seal the hole to prevent the aquifer contamination, and it bonds to the pipe. And it serves as an exchange medium between the earth and the pipe. Here you see inserting the trimming pipe all the way down for pumping the grout into the boreholes. And it is gradually, and it's put all the way to the bottom and then gradually pulled up from the bottom and filling any voids. Settling the grout can be expected. As the grout settles in each hole, it is refilled to the top. and then it is pulled out and put back onto the spool. This is what the diagram looks like of the header system with reverse return for cooling. Okay, and so here we see a 27 gallons per minute maximum flow going into the system. In other words, it's the red indicating the water is warmer. Okay, and it goes around and it goes into here we are in a 2-inch pipe coming all the way around, and then it can, as it starts into the other pipes, here's a 1-inch pipe coming down, 1-inch pipe coming down, filling up the boreholes. You notice that all of them it's all going into the boreholes almost identically in time, and then it's coming up, and of course it's showing in blue there, meaning that it's cooler as it comes back out of the ground, and it's of course mixed with the other ones as they come out of the ground. And this is referred to as a reverse return layout. Okay, it's referred to as reverse return. And so and then it goes to the heat pumps where it is going to cool your home. In connecting the boreholes, a trench, in this case it was 4 to 5 feet deep, 12 inches wide, and this is for the header pipe. All right, and all the header pipe was tight, actually taped on the end and plugged up to prevent dirt from getting into those. Here you see some of the socket welding going on, and the socket joints are usually stronger than the pipe itself. And here you see some of the butt joints going on to again put the pipe together. And the joints are considered to be stronger than the pipe itself because they're all fused together. There's no mechanical fastening underground in this particular instance. You notice there are 3 pipes in the ground here, all right, and that's caused from the reverse return, the way the reverse return is set up. And I'll just go back to that. You see there's 3 different pipes here. You notice those 3 pipes, all right, and that's what you see here in the trench, the 3 pipes. And here you see the pipes as one pipe is hooked on here and the other pipe is hooked onto another pipe. So it's not a continuous flow from one to the other. And that's the reverse return. And here you see it going into the building, into the utility room in the garage. And of course, the very last stage there, the header pipes are pressure tested to ensure no leak before they're all covered up. So this was left on for 24 hours, pressure tested. They came back the next day and it was good, so they started filling the trench in, all right, and trying to avoid heavy rocks on the pipes and things like that. And of course they mix the cuttings with the soil, and they locate it. Each borehole is located with the GPS. I also drew a map of the whole area to show where they're located, and I have that in the utility room. The ductwork is all installed because it is a new construction. All the ductwork was sealed, and then it was wrapped and properly supported. You see the support members there. The return and supply booths were installed in each room except bathrooms and kitchen to minimize pressure imbalances, improve privacy, and is quiet. So each room has a return and supply in each room. It's a big house. Again, the location of the heat pumps were on the second floor, and so these first 2 drawings are on the second floor. I have a 3-ton in one unit. This applies for the bedrooms, and then another one is the 4-ton unit, which is actually for the kitchen and for the large living room and other areas like that, dining area and so on. The 2-ton was used for the upstairs, the second floor. The second floor actually has a TV room and a computer room and another extra bedroom. Um, in the garage, the 2 pipes from the ground loop is used there, and of course this is where we will actually do any purging and flushing of the system. And there's one hot water tank located on the garage side. Now, the other hot water tank is located above the bedrooms for showers and the 4 bathrooms. Here we see the circulation of the pipes in the house. Here, this is in the utility room, and these are for purging and flushing of the system. And as you can see, these pipes are all put in before the flooring was put in. And everything's fused together, pipe connections, and made in secure manner. This is just showing the installation of those, the Tranquility 27 units, the 2-ton, what it looks like, and the 3-ton, and then the 4-ton. The 2-ton has one pump on the outside of it here, and the 3-ton also has one pump on it. The 4-ton has two pumps on it. I'll show you that a little more in detail in a minute. As you can see, here's the pipes coming from the ground. At this point they were not insulated, but later on they are insulated because all the pipes in the house were insulated. And particularly in the attic space, we wanted to make sure they're insulated. We didn't want to have any problems. So this is showing the actual heat pumps, and that happens to be on the 3-ton and the 2-ton heat pump. There's one pump there. On the 4-ton there are 2 pumps. This is showing the flushing cart, and this is showing hooking the flushing and purging cart to the actual system to purge the system, to clean out any trash that might be in the system, and to get out all the air out of the system. That's primarily what you're interested in. Here you see the connection of the de-superheater to the hot water tank, and this is the de-superheater coming from the hot water tank. This is going to the coming from the heat pump going to the hot water tank, and this is a domestic cold water coming in. And this was a 50-gallon electric hot water tank that I used. You can see the connection at the bottom going into the hot water tank. You see the hot water from the de-superheater is coming in there, and the hot water from the de-superheater is going to the hot water tank. Now, we began insulating. This is before insulation, and of course one of the reasons for doing that is to prevent any sweating in the attic, plus provide additional energy savings and to keep the pipes from freezing in the wintertime, since they are in the attic space. And this is the insulation around the pipes. As you can see, this is after they were insulated. And it has a programmable thermostat that is used to maintain your information about your heating system, and also to give you any alerts if anything goes wrong. This is showing a graph showing the first through the 5 years, and primarily looking at my system cost $45,321. A conventional system would have cost about $30,000. Tax credit plus $200, so the final cost around $29,922. Okay, so what kind of the first year, what happened to me? You know, the average electric monthly bill was about $145 a month. The second year it averaged about 150. The third year 156. The fourth year 164, 68, and then the fifth year was 164. So you can see there's a little bit of increase going on there. Of course, there was a little bit of an increase in electric rates. The plug load, the first year was about $92. The second year 77, the third year 83, the fourth year 88, and the sixth year was 79. So you can see my plug loads differed a little bit. I took the average monthly electric bill and subtracted the plug loads, and so it came out to be approximately $53 that first year, and 73 the next year, 73 the next, 80 the next, and then 85. So this gives me approximately what it costs to run the ground source heat pump system, because I got all the plug loads, my wife turning the electricity on all the time, cooking and so on. So there's a little difference. Now the average cost per square foot per year came out to be about 11 cents here that first year, 15 cents here, 15 cents the next year, 16 cents the next year, and 17 cents that last year. The projected cost per month was around $80. So you can see what my cost was, and it averaged out to about $73 a month. This is what the month-to-month electric bills were over that period of 5 years. So you can pretty well see, we had variations in temperatures. So there's going to be variations, but the overall average came out as shown on that previous graph. There's the first year, there's the second year, there's the third year, there's the fourth year, and there's the fifth year. Okay, now there's a little bit of variation. There is a summer rate in Stillwater, Oklahoma, around 10 cents per kilowatt hour. There is a winter rate that anything less than 600 kilowatt hours around 0.09, and then after that point it drops to around 6 cents a kilowatt hour. So you can see there was my electric bill for December. That was my high bill there. Okay, and then for the spring semester right there, springtime, that was my lowest cost per month for electricity. So you can see, even though the average was around 145, I did have some times when it was a little higher for this 6,000 square foot home. What if I get the latest ground source heat pump system that's out there? Well, Climate Master has a new Triology 45 series upflow package unit. It's a 3 tons. My current system should last for at least 20 years, so I'm not planning to change it out. But even in 5 years, things have changed. Instead of my 50-gallon, they have an 85-gallon smart tank that communicates very well with the thermostat and the system. And so it has 100% dedicated hot water heat exchanger and variable speed pump. That system would cost $15,500, 30% tax credit plus $200 a ton. My total cost would be about $10,000 to put this new system in. Now, the Triology claims that there is a savings of 30% more than the Tranquility 30 series. I have a Tranquility 27 series. So they're saying it's even 30% more savings. To heat an 85-gallon smart hot water tank, typically costs about $100, $186 to operate. And I have a 50-gallon hot water tank. Now they do have a 10-year extended labor warranty included with this. So, but it does not pay me to switch that out right now for that savings. It would not be enough savings for me at this point in time. But by the time my system gets bad, which theoretically is about 24 years, which is another 20 years or so, I still have a lot of savings to go. Now this is what the new unit looks like from Climate Master. And the methodology they're using for the communication with the thermostat to be able to control things from the heat pump to the hot water tank is what, to me, a very important item. More details can be found at www.youtube.com, and thanks for viewing this. And if you go to youtube.com and search for IGSHPA and videos listed as homes 1 through 6, you can actually see the installation of the system. Thank you. Now, we do have accredited installer workshops at IGSHPA in Stillwater. We also have accredited driller workshops. We have a building load analysis and pumping course. And we have what's called a CGD course, a Certified Geo-Exchange Designer course. We do have a new course called the Geo Inspector Workshop.